So this is the page. It was sent out to you guys. This is the top level page that gives you instruction for signing in. So, and you guys are already in the meeting, so we are using Zoom, so you do need to sort of quickly register with Zoom to get in, right? And it looks like you guys have all done that. That's very good. Setup instructions, if you want to run the labs. And also, we're asking you guys to kind of fill out your background a little bit. Just tell us a little bit about, are you a developer, data scientist? What's your background? So if you could just take a minute, tell us your background, because we like to customize this series based on your background. So if you could do that. And if you did this in the last time, that's fine. Just need to do it once. And also we are sharing the class folder with you guys. So right here, we just click on this, you would find the class folder and all the assets are going to come in here. And as you can see, so this is, we are dividing into session. Session 1 was here, session 2, today's session is going to be here, right? So everything here, these should be accessible to you guys. You should be able to get the slide decks and code and download it. Very good. And then, so this is being run by Elephant Scale. Just a very quick blurb about us. So what we do is we focus on training. The topics we train are AI, big data, and cloud. And all our trainers, work in the industry and have been teaching these for years. So we also run a lot of free webinars and classes like this one. If you guys like to be notified, just sign in here. And again, I will send you guys all the links right here, right? So that's that. And the sign up links, right, are right here if you want to get notified. And that's it. And also from the top level link, if you can scroll down a bit, you can see get this links to the individual sessions. Right, so today's session is going to be hardware accelerated training with Colab. And just click on this, and you should be able to see today's materials and links and everything. That's it, right? So basically, you just need to come to this one URL, and this is what I would, want to save this or bookmark this. This is it, and everything is basically follows from here. That's all the logistics, guys. So I'm going to hand this over to Mike, who's going to take it on. All right, Mike, it's all yours.
All right, thanks so much, Suji. I appreciate it. Good to see everybody here. Thanks for joining in. I appreciate it. Let's see here. Suji, do you want to make me the presenter?
All right, Mike. So I stopped sharing, so you should be able to share your screen.
Okay, let's jump right into it. Can everybody see that okay?
There we go. Good.
All right, awesome. Let's see here. I'm going to make sure that I have our questions and our chat window up, ready to go. Give me just a second to get set up here. So while I'm moving some windows around here on screens and all that stuff, I just want to give you guys a quick rundown of what we're going to talk about today. Before we do that, let's talk about where we started last week. So last week we did a tour of TensorFlow 2, right? We talked about some of the changes from TensorFlow 1 to TensorFlow 2. We talked about some of the reasons you might want to use TensorFlow and why it's so effective here, what the typical use cases are and why people like it. And it's kind of the king, it's the big dog on the block for production machine learning and deep learning. So while we learned how to build a neural network, we trained on the MNIST data set last time, which is kind of the hello world of deep learning. We learned how to do image classification on handwritten digits. And that was a bit simple. It used to be a world-class problem, but it is now very simple. And what we ended up doing was building a multi-layer perceptron. We learned a bit about how to put all that together. We also figured out how to optimize our data pipeline, right? So we got a good explanation of how we can use the TensorFlow datasets library to make our lives a bit easier. Now, it's important that we understood that stuff because we're going to start this one with the assumption that you all understand and know that here, okay? I do have the ability to answer questions, so feel free to post a question using the question software here or to drop something in the chat window. I will periodically keep an eye on those. So what are we doing today? Today's where it gets fun because we're going to build a much bigger convolutional neural network. And we're going to see how we can use GPUs, or graphical processing units, and TPUs, or tensor processing units, which are absolutely cutting edge hardware to speed up our model training. We'll also talk about some more basic modeling techniques here, like, for instance, detecting overfitting. We will create models that overfit quite often today. And we'll learn how we can use some specialized layers for techniques like dropout and batch normalization. We'll talk a bit about what those do, the intuition behind them, and we can figure out, okay, where do these fall in our toolbox for deep learning? Okay, so you have access to this notebook. However, let me go ahead and drop this in the share window here just to make sure everybody's clear with it. I'm going to drop a link in the Zoom webinar chat. Okay. And this gives you access to view it, but not necessarily write in this notebook. So as a reminder, if you'd like to code along with us on this here, then you'll need to, once you've opened this up, you'll need to go to File, and then you'll need to make a copy, right? So you can open in playground mode will do. It'll open it in your own playground so you can use it. Or you can save a copy to your drive, okay? And that will work. You can also download this as a Jupyter notebook offline here. Although I would recommend that you run this in Colab today, because Colab has access to GPUs and TPUs, and I highly doubt anybody has a TPU in their house they can use. So we're going to make use of some very professional, very big tools today. And because of that, we're going to use Google Colab, because Google graciously gives us a certain number of GPU and TPU hours per month. So Colab's awesome for that reason. So I'll keep. Oh, I'm sorry. Let me send that again. Looks like I sent that to only the panelists. I'm going to send that to the attendees here. So thank you. Good catch, Suji. Sorry about that, y'all. There we go. Okay, and that should allow you to open this up and clone it over so you can use your own. While we're doing this, let me go ahead and get this document up and ready here, and I'll add some notes as needed. Okay, and I'll drop the link in here as well. So we will share, we will copy link, and let me say, there we go. All right. So we're cooking with gas. Let's get moving here. Okay. So what are we doing here? We're going to be working on the CFAR10 data set. Now, the CFAR10 data set is something that was put together by a Canadian research group, actually just like MNIST was. A lot of the major players in deep learning all came from Canada, because there were a couple universities there that kept working on deep learning when everybody went down the symbolic AI route during what we call the deep learning winter in like the 60s and 70s here. So they're who we have to thank. You know, Jan LeCun did MNIST here, I believe. Joshua Bengio might have something to do with CFAR. But essentially, MNIST was a bunch of 28 by 28 pixel images that were black and white. These are 32 by 32 pixel color images. So this is going to be a good bit more complex for what our model has to do. And the reason for this is because it has higher dimensionality. You can think of dimensionality. We talked about this briefly last week, but as a quick review here, when you're working in a spreadsheet, your rows are your data samples, right? Your columns are your features. You can also think of those as dimensions, right? Because they're essentially, you can plot them as different axes here. If I have two columns, I can plot them against each other in an XY plane. If I have three, I can do an XYZ cube. Anything beyond that's hard to visualize, but the math still works, the modeling still works, right? So how many dimensions does, or what dimensional space is our model working in? Well, it's working in, where the data starts here, a 32 times 32 times 3 dimensional space, which is quite large. We're going to build a model that is much larger than our last model here, but we're going to make use of some more advanced modeling techniques. We're going to use feature extraction layers by using a two-dimensional convolution layer, right? I understand I'm throwing a lot of jargon at you right now, so I'll explain those as we go. If you have any questions, feel free to ask. And we're going to have some good times working through this. So let's start from the top, and I'll explain these things as we encounter them. We're going to start by importing everything we need here, okay? And I have this line commented out, but because we're using the TensorFlow datasets library, then essentially we can make use of the TensorFlow datasets package to give us a full list of all these datasets it can load for us. And once this import statement finishes here, it's got a bunch of stuff to download and install. We will see that there's quite a big list of open source datasets readily available using TensorFlow datasets, right? So here's just a massive amount of datasets that are already there. It saves us the work of doing pre-processing, a lot of pre-processing and loading and moving stuff around, which is challenging in its own right here. So we can see CFAR 10 right here. And this is, there's also a CFAR 100. So this is a subset of 10 classes from CFAR 10. There is a CFAR 100, which is harder to do. It's harder to train a model to differentiate between 100 different things than it is from 10. So we're going to do that here, and we see all this good stuff. Let's keep moving down. And this is the code, again, we use to load our data set. Notice that we want it, it's already split because this is a very common benchmark data set that people use to see, I came up with this new model architecture, how does it do compared to the rest of the stuff out there? They'll test it on data sets like this that everybody's used. So we start with a training set and a testing set, and we know that we're going to get those back because we're telling it to split. It's already split us for us into training and testing, so we don't need to do that. It's already randomized that, although we'll still shuffle. We do want the labels back, right? Because we want these labels split separately because we're doing supervised learning. So while we need the labels to be in the same order as our images, right? For instance, the label for the first item should be a frog, the label for the second item should be a truck, and so forth. We want to make sure that they're not in the same data set. I don't actually want to feed the model my labels as part of my feature set. Otherwise, it's just like giving somebody a test and handing them the answer key. And finally, the information. This is all the metadata about the data set, which can contain a bunch of useful things for us. So I've gone ahead and grabbed some of this stuff here, and we can delete that. And essentially, this cell is some code that we have borrowed directly from the TensorFlow tutorials here on CNN's. TensorFlow's got a ton of great documentation, and it changes and updates every week as they just moved to TensorFlow 2. They're writing new tutorials. So if the first time you run this, it's going to download the data set here. It might take about 30 seconds, depending on your internet speed. Looks like mine's pretty good today. It's moving. And then we're going to run the next cell just to visualize some examples. This isn't strictly necessary, the next cell here, this cell with the visualization. However, it's always a good idea to look at your data and get a feel for what you're working with. So this way we can tell some things here. It's moving, it's almost done here. And as it finishes up, we'll run this here. Let's talk about what else we're doing here. Oh, there we go. It's got the training set. Now it's shuffling them. And almost there. Awesome. So our data set's downloaded. Let's run this cell. Oh, whoops. I did need that code. Let me move that back there. Forgot I'd done that differently. Oh, this is going to download it again here. So this is just, again, you don't need to run this cell if you don't want to. It's just going to visualize it. It is hard to grab stuff from TensorFlow data sets. So I've actually stored in Keris's data sets package too. So I've kind of gone around TensorFlow data sets just to visualize it. However, this is the stuff we'll be using up here. And we don't need to go into this code here. This is just good old matplotlib. This is just creating a multi-grid of graphs here, and it's displaying each of these images. These are, in its mind, a graph. It's just representing them as, when we look at all the things together, we see the pixel values as a graph, we see an image. And to save memory, I've gone ahead and deleted those ones that I loaded just for this here, because this data is big and we need all the space we can get. So in review, those of you who joined us last week will probably recognize this part. This is a TensorFlow datasets training pipeline. We need to, anytime you're doing supervised learning, anytime you're doing some modeling, you typically need to normalize or standardize your data. So the most common example we talked about might be like z-score normalization, right? So that way you don't have things that are on different scales. You don't have the largest one overwhelm everything. So typically you do that by converting things to z-scores, sklearn, and all these other packages you might have worked with, have done this before. But we're working with images, so we can cheat, because we know images always have a value between 0 and 255, right? Because the way that pixel values are done is we say, well, how intense is it? And then for color images, we ask, how intense is the red? How intense is the green? How intense is the blue? So while our data set of MNIST images was a list of 28 lists, each with 28 numbers in them, our color data set here, a color image, is going to be a bit different. It's going to be a list of lists, but instead of having numbers, it's going to be another list with 3 different items. And those items, the first number represents the intensity for red. The second number represents the intensity for green. And the third is for blue. And again, they're all going to be between 0 and 255. So what we want to do is scale them between 0 and 1. This will let our model train faster. And we also need to convert our data to the data type that TensorFlow expects. Now, this is typically stored, I think it often starts as an unsigned integer or something like that. What we need to do is just use this function here, and this will turn it into a float 32, a 32-bit float. We'll also divide by 255. This will make our life a bit easier as well. Okay, so as we run this and we run that, I've got an error here somewhere. Sorry about that, y'all. Oh, I missed a, accidentally deleted a comment. Got scared for a second. Okay, so we can see that again, we've kind of initialized this here, and I had this canceled out. I'm gonna go ahead and move that back so we can go ahead and cache here. And what this does is we can see that we have some data set types here. What 2 data types are in our data set? Well, we see our images are float 32 and our labels are 64-bit integers, which makes sense. We have 10 classes. The labels are stored as a number 0 through 9 to correspond to it here. Now, we're going to do the same thing for our testing pipeline, but we're going to do it a bit different. You might notice, if you weren't able to attend last week, there are some differences between our training and testing pipelines, normally when we batch and when we cache. And if you aren't familiar with why, go ahead and take a look at the notebook from last week, as it does have a very detailed write-up as to why we do this differently. Okay, so those are set up. Now on to the fun part. Let's build a model. So I'm going to run these lines here. Again, as a quick review here, you're going to get very comfortable seeing these types of import statements here as you get into deep learning. We're working with a sequential model. What this basically means is I'm going to tell it the layers that I want in the sequence that I want them. So if I add, this for layer 1 and that for layer 2, and I do it in that order, then the model will have them in that order. And the order does matter, right? And we'll see this quite shortly here. So I'll have a sequential object. It starts like an empty skeleton, and I'm just going to start handing it stuff, and it's going to fill out. And it'll handle all the important things about passing information between the layers or backpropping error for me. Now, in our last class, we used these 2 layers, a flatten layer to flatten everything out into a vector, right? So if I have a list of lists of lists of lists, no matter how deep it goes, I could have a rank 30 tensor. I could always just flatten that into a single list, right? I could always say, well, what would this look like in 1 dimension? I could just squeeze it all together. And we will use this, but not as our, not for our input like we did for the last time. A convolutional neural network is awesome because it takes in matrices and it can work with them. It actually expects that. However, once we get these feature maps from these, which will also be matrices, then we'll need to flatten them into vectors before we pass them to the classifier part of our model. So these, what are these? Well, we have a Con2D layer. This is our two-dimensional convolutional layer. It's going to take two-dimensional data sets, right, or a matrix, you know, something with rows and columns, and it's going to look for patterns. It slides as stencil. Now, we're not going to go into the theory and the math behind what a convolutional step is. However, I will make sure to drop some really great tutorials and notes that can explain this much more deeply and with much better drawings than I could make into our Google Doc here. And I will add that at the end of the class. So if you have any questions, just feel free to drop them there. Now, I do see one question that came through here from Akash. He asks, what are the typical data sets that TensorFlow works with? Is it always image data sets? That is a wonderful question, Akash, and no, it is not. Images are a great place to start because it allows you to deal with like understanding the difference between like vectorizing your data or passing as a matrix, understanding convolutions and feature extraction, which are a little bit more easy to understand when you're working with images, because we can understand like, oh, this has an edge in it, this has a circle in it, this has a triangle in it, the types of thing these filters might be learning. However, you do not have to only work with this here. You can use TensorFlow for things like stock market predictions, which would be a time series analysis problem. I myself specialize in natural language processing, so I like to hand it sequences of words in order and do things like text classification or sentiment analysis here. Really, any type of modeling that you can do with a neural network, you can use TensorFlow for. You're just going to see a lot of images this time around because it's easy for us to limit the complexity of this to this style to save ourselves some time. But there are a ton of great tutorials here. So if there's a certain thing you're interested in doing with TensorFlow, I'd encourage you to look it up or feel free to shoot us a message here and we can help you out or point you in the right direction, okay? But that's a wonderful question. So it is not just images. This is just images for practice is what we're starting with, okay? So we're gonna see these two tend to go together when we're with the con for finding us features and this for reducing the dimensionality. The smaller our search space, the quicker our model is gonna do well, with some caveats, as we'll see. You can actually reduce your dimensions too much and lose good information. These two we're gonna use to fight overfitting. We wanna make sure that our model is not just memorizing the training data. We want it to actually learn things that it can generalize to things it hasn't seen before. And models will overfit. They will always overfit if you let them train long enough. So this is a good way to make sure that we can rein that in. We'll learn about that. And again, flatten is just reshaping our data, and dense is our traditional feed-forward neural network layer. This is your neurons that are taking in the weighted sum of all the inputs or all the outputs from the previous layer as inputs for itself, pushing, so converting that, it's just a dot product of weights and inputs, passing that through an activation function, which will capture nonlinearity, but essentially it's a squashing thing. And it will then pass that on to the next layer. So still kind of reviewing here, but with some new hyperparameters. You might be wondering, what are all these capital letters here? Why is he shouting at me? These are our hyperparameters. And we learned last week that it's a good habit to get into that, that not all neural networks are created equal. You need to change the hyperparameters a lot. And if you have the wrong hyperparameters there, it's not going to do as well as it could. It might do more harm than good. So there's a lot of experimentation in deep learning. There's no equation I can give you or function I can write for you that'll tell you exactly how many filters that this should have or how many neurons that this layer should have. So you have to try and try again and train and retrain on these things here and compare and contrast until you say, well, I think this is going to be best. So there are some features here that we did not see last week, mainly these ones that say filters, these hyperparameters, excuse me, I keep saying filters. These hyperparameters here around how many filters, you can think of this as patterns. Filters is a pattern. How many patterns is it going to learn? And how many and how big should they be? So I'm telling it, go ahead and learn patterns that are 3 pixels by 3 pixels. I want to learn 3 by 3 grids. I could make this 4 by 4, 5 by 5. Typically you see it stick to odd numbers. Just kind of go ahead and it's going to slide over each 3 by 3 block here. And we'll talk about that. These are some parameters you can change here. We won't go too deeply into it because we've got a lot to cover today. We have max pooling, which is going to basically pool 2 by 2 grids, right? So if I have, kind of 4 pixels in a 2 by 2 setup, it's going to take the one with the largest value and replace those 4 and just say, okay, I've reduced it here. This cuts our dimensionality, and this is absolutely magical for deep learning because when you have these very high dimensional inputs here, that can really slow you down. There's something in deep learning or in machine learning in general called the curse of dimensionality. The more dimensions to your data set, the more columns per se, right? And again, in an image, every separate pixel is its own dimension. Then essentially, the more dimensions in your data set, the more data you need for the model to fit it correctly. Now, this is true of neural networks. This is true of decision trees. This is true of support vector machines. Any other machine learning model you might have heard of here, the more dimensions is typically bad. It contains more information, but it's much, much harder, right? And the way I explain this here is I say, well, if I give you a 10 by 10 spot and I say, hey, there is treasure hidden in this 10-foot by 10-foot spot here. And you're able to search through it 1 foot at a time. Okay, you can probably get through that. And if I say, well, it is 10 feet by 10 feet by 1,000 feet deep, that's going to take you a lot longer to search. And in that same way, finding that decision boundary that allows your neural network to classify and say that, well, if it's on this side of this line, it's probably a dog. And if it's on this side of that line, it's probably a cat. It's searching for that, and that's the treasure it's going for. And the more space it has to cover, the longer it takes. So by reducing our dimensionality, we're basically taking advantage of a trade-off. We're saying, well, we're going to make the image smaller and grainier and harder to see, but we can still tell, right? If we go back up to these images, that is not the most crystal clear picture of a bird right here or a horse in row 2. And yet we can still tell. And it turns out our neural networks can too. And if we made this even grainier, it could too. And that is a smaller version. A grainier picture is a smaller picture, right? Less pixels makes it less crisp, but it's still enough to figure out what the heck it is. And obviously there's a point where, if you reduce this to 5 by 5, I don't know what that is. It's much harder to see. So we will see there are limits there. So we've set some very common parameters here, and these are things you can play with. And I encourage you to do that here. One thing that is very important is that you use a ReLU activation function. Now, again, we're not going to go too deeply into this here, but a ReLU activation function stands for rectified linear units. And this was absolutely magical when people found this out here. You might have seen sigmoids before, or tanh, which is a hyperbolic tangent function. And what we find is for this specific task, for computer vision, ReLU is worth its weight in gold. For other tasks in general, ReLU is still probably the most effective activation function out there, unless you're working on something very domain specific or something where you need kind of a low end, a high end, a neutral area like sentiment analysis. There you would use something like tanh or tanh. So rectified linear units, what are they doing? Well, any neuron that outputs a negative value, it's just going to replace that negative value with 0. And any positive value, anything greater than 0, from 0.00001 or whatever, all the way up to positive infinity, that will be set to, it'll just pass that value on through, right? And this is helpful, right? Because from an image, to me, I think this makes a lot of sense here. And this, you can generalize this next statement I'm going to make to information theory overall. But the intuition I find behind ReLU that I think is really helpful is that if I have people looking for patterns, right? So I have all these filters up here, these convolutional filters. You can think of these as people. It's like I've hired 64 people, and their only job is to shout when they see the pattern that they're hired to look for, right? Well, this is great, but the way a neural network is normally structured, people are going to do, it's going to do some math, and it's going to pass that answer along to you. So if the number is very high, let's say 10, I know, oh, wow, this really looked a lot like that pattern that you know, person number 1 in my filter set is hired to look for. But is it helpful to know, you know, that if it's a 0, I know it looks nothing like it. If it's a negative number, that almost doesn't make sense. It's not useful to me in any way. If I hold up a circle and I say, does this look like a triangle? Saying no is enough. I don't need a numerical measure of how much this circle does not look like a triangle, right? So what ReLUs do is they cancel out some of the noise. You know, if I have those 64 filters, those 64 people telling me, and 3 of them, they lit up a lot. They saw exactly the things that they're supposed to see. That's useful to me. I don't want them drowned out by the other 60 or so people who said, well, actually, it looks nothing like mine. Let me tell you how much it looks nothing like mine. So ReLU zeroes them out. It turns out, it quiets down the neurons that aren't telling us useful information, and it lets only the ones through who are telling us useful information. And that's great to have. Now, for this first training, we're going to set it to 5 epochs, and this is going to take a while, okay? I'm going to go ahead and, oh, whoops, I forgot to run this cell. Got to run those, okay? And this model is going to run naturally on the CPU. And I know this because I haven't enabled a GPU runtime or a TPU runtime. Those do not happen on accident. Those are expensive, although Colab gives us a certain amount for free. So I want us to benchmark today to see what is the difference between using a CPU and a GPU and a TPU. So you can start to get a feel for going, you know what, this is worth the money, this is not, and kind of figure out what is most useful to you and your company, okay? So I've built the model here, and you're gonna see a pretty common design pattern here where we go conv, ReLU, max pool, conv, ReLU, max pool, right? This is basically saying, learn the filters, right? And again, the neural network is going to learn what filters are most useful. I'm not telling it 64 different shapes. That's not stored in memory somewhere where, you know, you get a circle and you get a triangle and you get a square. It's going to learn what's most useful for the data set. So these are learnable parameters, just like in any other neuron here. And so I'm going to tell it, you know, I want this, and I learn these filters, and then quiet down the ones that aren't helpful with ReLU. And then once you've built these filters, this is going to output a filter map, right? So the output of this specific layer is going to be 64 different feature maps. And it's going to be a map of basically saying, it's almost like if you were sitting in a stadium and I said, hey, I want you to be a feature map for people with brown hair. Go ahead and look at every seat in this stadium, and I want you to write a 1 when the people and the person in that seat has brown hair, and I want you to write a 2 if it's really dark brown hair, and I want you to write like a 0.5 if it's like light brown hair, and I want you to write a 0 or a negative number if they're blonde or redhead or something like that, right? And if you did that for every seat in the stadium, you'd have a map at the end, right, to tell me where all the brunettes are sitting, all the people with brown hair, and some of those aren't useful to you, right? So what I might, you know, if I find some pockets, right? If I'm looking for a pocket of people where there's 40 people with brown hair, then max pooling is really useful because it reduces the dimensionality. Basically, I'm saying, you know, go ahead and turn down the resolution on this map, turn down the resolution on this image. And that reduces my dimensionality, right? So filters, ReLU, max pool. And then what do I do? Well, I want to see if there are any patterns inside my map of patterns, inside my filters. So I'm going to run a conv layer on the output of my previous conv layer, which has been max pooled. And you'll see this. So what you're doing is not just creating a map of where all the features are, like, you know, maybe edges or corners or rounded things, or maybe it's gradients or shading, or, you know, it can learn all these things, and they typically do. Then essentially it's going to say, okay, I have these feature maps. Now create feature maps of my feature maps. Are there common features we're seeing that show up a lot across some of these things here, right? And again, it's doing this not just for one image at a time, but it's going to do this across every single image in the entire data set. And we're still doing conv, relu, max pool, right? Now, once we've done this, we turn around and we say, let's go ahead and flatten it. So what I have output here, what's being passed to my flatten layer? It is those 128 different feature maps that got pulled out from here. And these are maps, these are features of features, right? So it's kind of looking at the overall thing, all right? It's looking for the high level. And then we're shrinking it again, and we can see this here. It starts off, we had a 32 by 32 image, and then we had 64 features, right, in the first filter. So we see typically you lose 2 per, depending on the size of your filter, your step size, a bunch of things that we're not going to go into too deeply here, but I will make sure we add some links to if you're still learning the theory behind this. So we went from 32 by 32 to 30 by 30 by 64, and then we max pooled, and we see the output of the max pool, it cuts it in half. That's great. It drops our dimensionality. And then we go from 13 to 13, right? We drop by 2 again, and again we put 128 here. This is a number. These are actual parameters we set. How many filters, right? It's like a folder of different features. And we max pooled again, and the thing it's getting is it's getting 128 different 6 by 6 feature maps. We flattened that, and that turns into a vector, right? We just concatenate all of them together. We just line them up. You know, all 6 by 6, we just turn them into rows, and we line them up, and we end up with a vector that is 4,608 elements long. We feed that to our classifier, just like we built last week for MNIST, right? And this is a really big operation, right? Look at all the trainable parameters here. It's the vast majority of it here. It's about 90% of the network. And this model comes out to have 1.25 million trainable parameters. Now, this is a lot when you realize that all we're doing here is a very fancy, like, you know, essentially regression. Deep neural networks are just essentially regression built of regressions, right? Which are themselves built of regression. That's really all we're doing, right? And when we combine all these things with some activation functions and put it all together, we end up here with a lot of trainable parameters. I see a good question from Lu Sheng Zhu, who says, what is the difference between conv1 filters and conv2 filters? Great question. Essentially, these are just the numbers I picked. Typically, you keep things to powers of 2 that can give you some speed up time there. It's not urgent. You don't have to. I could do these as 63 or 65 or whatever. But essentially, I kind of picked some things here. And I said, these are the raw features, right? And then this is that. So these are for different layers, right? And again, the model would still work if I pulled these out. I could absolutely just, you know, comment out one of these and still run it. It would change the architecture, which would change the performance. But these numbers here, I was just starting with an intuition. Let's probably 64 patterns they can find in the image. And then I want 128 different maps of the patterns in the images, right? So I want to know if I see some patterns that, you know, it might learn some patterns that have to do with what a wing or a wheel looks like, because we have airplanes and trucks and cars in that data set. But it also might learn some things like what a horse's leg or the eye of a frog looks like here, because again, those are in that data set too, right? So I'm looking for patterns that, you know, well, the eyes and wheels both have curves in them, and they're both going to light up the curve filter that our model will probably learn. And so what happens then? Well, they're probably going to be, you know, different in the way they light them up, or the way they line them up, or maybe where they appear in the image. So this one is going to learn that, right? As you get deeper and deeper, it's going to learn higher layers of abstraction. So one way to think about this is if it was learning faces. This isn't 100% true, but it's a good way to learn kind of the gist of what a convolutional neural network does. You could think of the first convolutional filter here, this conv layer 1, as learning shapes, lines, edges, things like that, right? And it's going to learn, you know, lines that are pointing at different angles and things like that. And we actually, this we found all the way back when a couple neuroscientists named Torsten and Wiesel were looking at a cat brain, and they were showing it different images, and it wasn't lighting up. And then it saw a line that was at one specific angle, and that made the neuron light up. And they realized, oh, wow, this neuron is only looking for lines at this angle. And they, you know, shifted the angle, and they saw another neuron light up. And they tried rounded things, and they saw another neuron light up, right? So that first layer that's in our neural network, and also just got like the first layer in your eye, right behind your eye, it's looking for basic shapes. They're the building blocks of things we're looking at, right? Our face is nothing but angles and curves. And then if you go to the second layer, well, it's going to look for patterns in those layers and curves. And we're going to realize, well, a nose kind of looks like a triangle. And an eye kind of looks like an eye, like a circle, but it's not perfectly round, right? And then if you went deeper and deeper, all right, if you're extracting more and more features, you'd see the next conv layer learn to do things like both eyes together, right? And maybe a nose and ears. And it's starting to put these things together. And then eventually you'd see one realizing, well, you know, where are eyes in respect to the nose? And, you know, a nose should be under the eyes, not above, or they should only have one nose, not four, or things like that, for this to be classified as a face. So the deeper you go, the higher this combination of abstractions here. So if you're asking what are the difference between what are these two filters doing here, this one is learning higher order features based on what this one found. Okay, if you're asking about the numbers, these are just some numbers I picked. I just wanted to vary the size a bit here and see how things change. I would encourage you to change these numbers around and run them and see how things change. And this will help inform your intuition of a lot of things here. Great question. I see another question from Akash who says, when dealing with CPU model, is it always the process of con2D, ReLU, and then max pooling? That doesn't matter if you're running CPU or GPU or TPU. It's always going to be the same. Your model architecture will not ever change depending on that, although some of the boilerplate code might, right? So that's a great question. You will not ever write your model this way for a CPU, which is just like what you get if you run it on your laptop, versus this way for a GPU, which might be your desktop that has like a really nice NVIDIA gaming card in it, or in the cloud here. All right, very good question. However, when you're building a convolutional neural network, yes, you will always typically use the pattern of conv, ReLU, max pooling. Now, you don't always have to do a two-dimensional convolutional neural network. Let's say you were building something to classify if somebody, you think of like the EKG data when you see somebody in the hospital and you see that thing that beep and it shows like a spike and shows their heart rate. That's an EKG monitor. That you could run a one-dimensional convolution over, right? That's data and it's an image. It's just one-dimensional rather than two, right? Because we're just taking one number and we're basically reading the spike, right? How's this value changing over time? You can do a three-dimensional convolution. So when you get an MRI scan, that is actually a three-dimensional image. And there's all kinds of great competitions on Kaggle that you can look at where people have written all kinds of code that use like a conv 3D to look at this MRI and say, aha, I found a tumor. Or here's this issue that we're looking for, or something like this. So because it really depends on the shape of your data. So images we're looking at on a screen, two-dimensional. If you have three-dimensional images from things that are more advanced like an MRI, you'd use that. You can do for things like stock prediction, you'd use like a conv 1D, a one-dimensional convolutional layer. People will also do that for patterns in language. You can structure language that way. Great questions all. So let's continue here. So I've built the model. I'm going to compile it. We've seen that it's quite large, okay? And I'm going to run it. And we're going to see This model takes a bit of time. Oh, whoops. I need to change the GPU model.fit. Change some names around. I forgot to update it here. Well, let's see what our error is here. Input of 0, layer sequential 1. Oh, this is an easy one here. So it's expecting it in one shape. It got it in another. So let's take a look at what's happening here. My guess is that I didn't normalize these things the way they needed to be, or set this up here. So it says it's 32 by 32 by 3. And if I want to build that into the model, well, I guess that's important here. So I'm going to say that, and I'm going to say input shape equals, oh, wait, I have that over there. Sorry about that. Okay. It's got that 30 by 30 by 64. This happens sometimes, y'all, so don't sweat it. We are going to just come back here, and I'm betting I accidentally ran something twice. So why don't I do this? I'm going to restart a runtime. And luckily, since I've already downloaded the data once, it'll be cached. I won't need to download it a second time. But I'm going to go ahead and rerun this here. I'm glad this happened because this is the most common error you will have to debug in deep learning, is that the shapes of your data and what the model expects and the vector and all that good stuff, they're actually not in the shape they need to be. All right, so we built that, we built that, we built that, we run that, we run this, and let's see if it gives me the error. Nope, okay, I had just run something too many times here, and that's why the shape was wrong. So we'll see that this model is going through, and again, we're running our data on batches here. So when you see 391, my data set is much larger than 391 images. That's 391 mini batches of images. And if we look up at our data pipeline, we see that each batch is 128. So I'm training on 128 times 391. And this is a big neural network. It's got a couple, it's got 1 million or more parameters here. So as we kind of see, this is going to take a little while, right? This is about 2 minutes an epoch, and we'll see, we'll get decent performance. We'll get to about 70% here. We can kind of watch this thing train, but this is one of these areas where they say if you're going to go into deep learning, or you're adding a deep learning team to your company, make sure you have a good coffee maker, all right, or a good water cooler, because they're going to hang out around it a lot as they're waiting for these things to train. Now, we're going to see how we can speed this up greatly using GPUs and TPUs. And we're going to talk about when you should use one versus the other, because a TPU is about 10 times as expensive as a GPU. They are not cheap. Right, so to use here. Luckily, you can pay by the minute with cloud platforms like AWS and Google Cloud and Azure. They all, I don't know if Azure has their own TPUs yet, but I know AWS and Google do. And they're really cool. As this keeps going here, you can kind of get a feel for just how slow some of these larger models can train, right? And this brings us to an interesting point about some of the models you might use in production. As I said, my specialty is natural language processing. One of the most popular models in the NLP world right now are very, very large transformer models, typically called BERT, right? It stands for bidirectional encoder representations. I forget what the T is, whatever. Essentially, that model has billions of parameters, and the operations it's doing are much more time intensive than a convolution operation. Convolution operations take a good bit of time, but what some of these models are doing here, like to train on a model that takes much larger, and it's doing much more computationally intensive things, and then they're turning around and training it on literally every page on Wikipedia across every language. That model takes forever to train. It's just not feasible, right? If your boss asks you to solve this problem, you can't say, yeah, I can do this. I need to train a model that's going to take 7 years. Well, you're probably not going to keep that job very long. Models that are not feasible to train on the CPU, which is doing, you know, basic addition, one number at a time, just like, you know, this is how computers work under the hood. That's not feasible, but a GPU can do this and distribute the training. It can say, hey, I'm going to take these first 20, you take the next 20, and you take the 20 after that, and then we're going to combine our results. It can do that across many, many, many cores, and we'll see the speed up is going to be incredible. So our first epoch here took about 151 seconds. We'll see that when we switch to GPUs, our epoch is going to take, you know, more like 7 seconds, 10 seconds, something like that. So I'm going to let this epoch finish here, and then I'm going to actually pause this. We don't need to get through all 5. We get the point, and this is painful. We'll visualize how it does, and then we'll look at the GPU here, how to enable that, and we'll get to the fun stuff here. All right, so almost there. Let's talk about, we got this here to visualize it. And this is if we visualize it. We're going to run it later across. This was actually on the GPU, and I was able to run it for 20 epochs, and it ran faster in 20 epochs than this model did for 1. And we can see that, you know, the model was getting about 70%. We do see, can anybody tell me, you know, just in the chat window here, I see that my training is getting up to almost 100%. And my testing is staying at about 70. Which one of them is correct? So essentially, the training is getting better and better because the training is it's memorizing the answer. So unfortunately, we do not want the training to do that here. Your testing set is your North Star, right? That is how well it can do on data it hasn't seen before. So why is the model getting better each round? Because it's practicing on the exact same set of data. It's getting shuffled around to different orders and things like that. But if somebody asks, you know, hey, my training accuracy was this, my testing accuracy was this. If somebody asks you, how accurate is your model? The answer is the orange line, not the blue one. This is actually a bad thing, and this is what's called overfitting. All right, I'm going to go ahead and pause this one here. Well, actually, let's talk about overfitting while that finishes here. So this blue line here, you can see they're both going up at about the same rate. And again, loss is just the cumulative error, right? We can see they're both, you know, the error is going down, the accuracy is going up. But at some point, our training accuracy keeps getting better and our testing accuracy kind of flattens out. And we can see our loss, our training accuracy continues to decrease, whereas our testing loss, it goes down, and then the more this model overfits, the worse it gets. If I let this continue to do this, we would start to see testing accuracy drop. So it's overfitting to it, and it wouldn't generalize well, right? So we want to avoid this, and the way we're going to avoid that is by adding in some layers once we switch over to GPU and TPU called Dropout and Batch Normalization. And that's going to regularize our network. Some of you all might be familiar with linear regression or polynomial regression or something like that. You got statistics background, you study this in college. And you might have heard of regularization. And regularization is a way to penalize the model for complexity. And generally, this is a bunch of added complexity it's adding in to memorize not just how to figure out if it's, you know, a car or an airplane or a frog or a horse, but if it's that specific one from the training set. It's memorizing the littlest features here, like what is the pixel value in the top left corner? Well, that's not useful to the real world, but it might be useful to helping memorize a training set. So we want to avoid that here. And when we do that by penalizing it, we'll show how we can use dropout and other things to do that. So I'm going to go ahead and stop this cell. All right. And let's go ahead and visualize this guy. Oops, CPU training history. What did I call that? CPU training history. Oh, we're not able to plot it because I didn't finish the execution, unfortunately. Oh, well, we're going to go here, and it's not worth our time. We can come back and do that later here. So luckily, this function is It is here where it is learned. We're good to go. So now let's talk about how to enable GPUs. This is the part that you guys are most interested in. Let's jump right into it, okay? Well, you can use GPUs to speed up your training a good bit here. You'll find them in servers that you can pay for on Amazon Web Services or Google Cloud Platform or Microsoft Azure. There's also other companies like Paperspace and all these other ones who are great for this here. And they're all kind of the same, right? They're going to have different billing models. They're going to try and compete and tell you how they're different. But really, at the end of the day, if you can do it on one, you can do it on any of them, okay? Now, one thing that's really cool about Google Colab is that you can get practice on these things or use them for free, right? So we're going to turn on GPU Runtime right now. We're going to do this by going to Runtime here. And I'm going to go down to Change Runtime Type. And I'm going to go ahead and go from, oh, whoops, I had that on TPU the entire time. I'm going to go to GPU, okay? So it was on TPU, but to be clear, this was still GPU training. I did not write the code to enable TPU training. So these were CPU, too many letters here. These were CPU training times here. We'll see it takes about 10 seconds per epoch with a much, much larger model with a TPU here. GPU will be even faster. And we'll talk about why. So again, I went to Runtime, change Runtime Type. Yours, if you're just opening this up, is probably set to none. You're going to go to GPU. Now, you might look at this one too, Runtime Shape. Is it standard or high RAM? The only time you would ever use high RAM is when you have a massive amount of data or you're doing something that takes a ton of RAM. This is not something you'll need to touch. So typically don't use this one. This is, again, Colab is free, but there's no reason to pay for extra memory and they're not going to give you much. You'll burn through that real quick here. So I'm going to go here and I'm going to hit save. So Python 3 GPU and standard, I hit save. Now this is going to reset my kernel and that's because it's training me on, it's moving me to an entirely different server. You know, my code is running on someone's computer, just not mine. It's running on a server inside a Google data center somewhere. And when it's doing CPU, it's on one. And when it's doing GPU, it has to move to an entirely different one. So everything's reset. So I'm going to go ahead and go back up top. I'm going to run this, and I'm going to rerun these cells. And I'm going to go through here, and we'll see this model is going to train much faster now. Now, the downside is that because it moved me to an entirely different server, it does have to download and shuffle the data again. This is just something that happens because it can't be avoided because you move to a different server. However, it's moving fast. All right, and that was all the training images have been written and shuffled, and now it's doing the testing. And we're moving. All right. And we're through our pipeline, and now we're on model training. Now I want you to see the difference here, all right? And it still says CPU model, however, it's running on the GPU now. And we see our runtime, the first epoch, it took 151 seconds before. This one's gonna take about 10. And that's for 1,258,122 trainable parameters. That's a lot of learning there. It took about 18, and now it's going to go real fast once it's gone through because it's optimized everything. And this moves fast. Okay. So great benchmark here to see what a difference this is here. It is CPUs you can run some basic models on, but man, it is really worth the money to train on these things here. Whoops. Training history. This should be just, let me rerun this here. There we go. Okay, so we see now our model is, it got there. It's overfitting starting at about epoch 3. Obviously, there's no such thing as half an epoch here. It's just connecting the dots for us here. There should be 5 dots on the graph, and we didn't tell Matplotlib to do it right, so it did it this way. So we're getting to about 70% performance, which is good on the CFAR10 data set. This is a very hard data set. This is not a data set that you will get to like 96% on. I'm not sure what the actual benchmark is. I think it's maybe high 80s for like, or maybe not even, maybe mid 80s for like the really big like Inception V3 or ResNet things that you see, you know, that take days to train on GPUs. They don't get to 100%. So the model moved really slowly. Now it's moving fast. So now we can iterate on some things here. But before we do that, it's very important to understand how we can use this GPU and get some info about it, double check that it's ready. You know, it's important to, it's very important to get a feel for like what models are we using, what hardware are we using. There will be times where you try and train on a GPU and it's going really slow and you're like, what the hell? Well, it turns out maybe it wasn't set up correctly and you need to do some stuff. So let's talk about how to debug and investigate these things. So when we talk about a GPU, that stands for Graphics Processing Unit. You might have heard the term graphics card before. There's 2 major players in the industry. There's AMD and NVIDIA. Now, just having the GPU isn't enough. You have to have some really specialized software that TensorFlow is nice enough to bundle in for us. This software was written directly by NVIDIA. It's called CUDA. And it does all of the distribution for all these crazy vector calculus and linear algebra operations that are happening under the hood. So it makes it so GPUs can do matrix multiplication, which is all neural networks are under the hood. It's just a ridiculous amount of matrix multiplication. It can do those for us much, much faster by distributing it. We do not want to write that code to have to tell it what parts of the matrix get multiplied on what cores and how to, you know, how to break the work up and then how to get it all back when they're all done. Luckily, NVIDIA has done that for us. So when you're using a GPU, you pretty much have to use an NVIDIA GPU. AMDs are just not up to par with it. There's some open source things there, but they kind of suck. NVIDIA is really the only game in town right now. So when you're using GPUs, that means that you're on a machine that has NVIDIA drivers. If you have NVIDIA drivers, you probably have this command line tool, NVIDIA SMI, installed. So what is it? Well, it's really just telling you what your machine is, and it tells it some statistics. So we are training on a Tesla P100, and it tells us the power usage. It tells us how much RAM is occupied versus how much it has total. This is really good. I think this is a 12 gig card or a 16 gig card, something like that. It's a lot, but that's really good. This is fast. So there's a single GPU that we're using, not multiple GPUs, although you can do that too. And it is a fast one. This is really powerful. So one of the best things that I like to do is to double check. If I'm going to train on a GPU, I want to check, well, is TensorFlow able to access that GPU? And if it can't, that's my first hint, something is wrong. So inside the test module in TensorFlow, there's a method called isGPUAvailable. And if we run it, it'll return a Boolean, true or false. If it's true, then good, you're all right. You can train on GPU, you're good. When you run the model, it will run it on the GPU. If it's false, then for whatever reason, you're using maybe, if you're using TensorFlow 1, there was a different version of TensorFlow versus TensorFlow for GPUs. TensorFlow 2 does not have that problem. It could be that. It could be that it wasn't built correct. It could be a lot of things, right? But this is the first thing to tell you. It won't tell you how to fix it, but it will tell you what to Google, right? Now, this method itself is being deprecated, even though I really enjoy using it for this here. I think it makes my life easier. They actually tell us to use this one, which is tf.config.list physical devices. And if we run this, these are the actual devices that TensorFlow can use to run computation on. What are they? Well, these, when we see name equals / physical device : CPU, whatever, or GPU, this is the CPU inside the server. This is the GPU. And then the XLA is actually a library that allows your code to work on a GPU. You don't have to use it. You don't have to know much about it, but it's there, right? So you're there, even though you're seeing these two XLAs, they don't count. It's the GPU and the CPU that matter. The fact that the GPU is here means TensorFlow will grab it and make it work. So let's try rerunning this here. And we do all this here. And instead, I've changed the epochs to 20. So let's see what happens when we train for 20 epochs. The model got to about 70% performance on our test set in 5 epochs. And it looked like it started to overfit. Let's crank it up to 20 and see if that's really happening here. Okay. So I'm going to run these, run that, run that, run that, run that. Oops, name model is not defined. Oops, should be GPU model. And that is fast. Sure beats sitting around for 2.5 minutes per epoch here. We're going to come out to about 1 minute in total. So we can do 20 epochs with the GPU and the time it takes to do half an epoch without it for this specific model. Now, again, your runtimes are going to differ depending on the structure and how large or small your network is. What if you're doing a lot of convolutional operations, those are computationally intensive. They take a lot of time. So it really depends, right? Now, we're moving here, and it looks like it's starting to overfit, right? I can see my validation accuracy is pretty much stuck at between 68 and 69%. But my training accuracy keeps going up. It was 94%, 95%. This is gonna, so it's really memorizing the training set. It's memorizing the practice test and not doing as well on the real test, right? And we can see as it starts to overfit, you know, if you're not worried about overfitting, you will, who cares? Let it memorize the training set. I will show you, you should care because what do we see here? Well, we actually see, if we run that, test sets is starting to drop at the end there here, right? We're going back down to 67%, right? So the more you overfit, the more you're, you know, it's like if you had data on 10 customers and your model overfitted to those 10, that model is going to get really good at predicting those 10, and it might not target other customers who are like them because it's only worried about those 10 specific ones, right? So that's overfitting, and that can actually absolutely hurt you here. And we can see, yeah, our loss, our error spiked whoop, right back up, right? So by about epoch 6, it had learned all it was going to learn for our test set, and everything beyond that was memorizing. So how would I use that in practice? Well, I would stop training by probably epoch 6, right? It looks like that's actually the peak of our performance in our training set. Now, obviously, yeah, testing set. Right here, this is the highest point. It's starting to kind of peak out there. I would either cut off here or back here somewhere before it diverges and runs away. So we're overfitting. Let's stop it from overfitting, okay? So I've got this section on overfitting here. We're going to train a second GPU model, and we're going to add in these dropout and batch normalization layers. Now, how can I give you a quick 30-second explanation of what these are doing here? Well, dropout is quite literally that. It's saying, so dropout of 0.5 means that for every single trainable parameter in the layer before, right, every neuron here, right, so coming from this, well, it's actually going to be from this one here, there's a 50% chance we're actually going to turn that neuron off, right? It drops out of the game for this round of training. And every epoch is going to be different. Every epoch, it flips a coin and it says, hey, I don't know if I actually need you or not. And what that does is it makes sure that maybe your neuron is fitting to some things, and it's overfitting to some things that are helpful 80% of the time, but you know they don't help the other 20. Well, that's going to cause your other neurons to not learn a lot because you have a star player, right? You know, if I put you on a basketball team and had you go compete with, you know, with 4 other people around your level of quality, and you guys practice, you practice, you practice, you get better at basketball. If I put you on a basketball team with 3 other people and LeBron James, you would not get that better because LeBron is so much better than everybody else. You wouldn't get the ball that much. You wouldn't get many opportunities and things like that, right? So essentially, that's dropout is going to bench people randomly. Some of that time, it's going to be LeBron. Some of that time it's going to be you. Some of that time it's going to be other team players here. And what that does is it makes sure that everybody gets more practice working with everybody else, right? And this stops your model from overfitting, because at any given point, the neurons, that if I'm a neuron, I'm getting inputs from neurons in the previous layer. Well, the layers that I had last epoch and the layers I have this epoch are different. So how can I just start listening to only one person? How can I start overfitting to that? I can't. So I have to be a bit more selective. Let's see here. We are moving, and so I see that Darshan has said his is taking 18 seconds per epoch, even with GPU. Yeah, that's quite possible. It depends on the machine it puts you on. It depends on a lot of things. Depends on network traffic at the time. That could be part of it. So you will see it here. Obviously, it's nice when it's like a 3-second thing here, but it could also be, I mean, there are some computations that are happening on your machine too. It could be a lot of things here. So 18 seconds isn't as fast as 3. However, it is still significantly faster than what the CPU is there, right? So that was 2 minutes and more and change on my machine there. So don't worry about that. It is still a great speed up there. But good question. Okay, so I've gone ahead and added these in here. That's what Dropout was, right? It's making sure that, you know, LeBron isn't a ball hog and that everybody can learn everything needed. And then a batch normalization layer. Now this one is a bit harder to understand if you don't have a background in supervised learning or machine learning, but we can explain it pretty easily here. So we're going to randomly grab a bunch of data, right? And we want to normalize our data when it comes into our model, right? So that's one of the first things you do. One of the first things you learn in machine learning is you always want to normalize your data. We talked about z-scores or things like that, all these other ways. Well, your data starts normalized, right? So it's normally distributed, which is great, and models do really well with that. But as it goes through, our weights are random here, right? Then what can happen is you can get some weird peaks and spikes, and it's going to shift your data. It's going to kind of veer. And that's a problem, right? So your model's going to have to overcorrect to overtake that. And that takes longer, right? So what batch normalization does is just like we normalized our data, right, around the mean, right? So how far are you from the mean of this, this dimension or something like that? As we normalize our data before the network, anytime you see a batch norm layer, it's actually going to normalize the data again. And what that does is it keeps it nice and normal all throughout. It doesn't let it kind of drift one way or the other to where it's not normal anymore, and it slows down your training. So it'll converge faster. It'll get there quicker. And it does have a slight regularizing effect. It does slightly penalize the model for learning things that aren't really useful. This is very well explained in some blog posts and in the white paper where it's found. We're not going to go into it today because that takes a very deep understanding of linear algebra, but it's here. So I'm still doing conv, relu, max pool. I typically add in a dropout layer and a batch norm layer, and or. You don't have to use both. You don't have to use them together. But you're going to, typically you're going to batch normalize after your dropout. So I'm going conv, relu, batch. It should be conv, relu, max pool. And then you kind of see these together, and then I'm going to drop out. Then I'm going to normalize again. Why? Because it's going to get fed into another network that's doing important stuff here, right? So then again, conv, relu, max pool. And what do I do again? Drop out, batch norm, okay? This is the end. So all of this is our kind of our feature detector, our feature extractor. It's learning different features about what to look for in the data, right? And because we've learned those features, then our classifier, which is everything here through here, right? I'm gonna mark this out. Start of classifier. This is the end of feature extractor, right? And this is just super helpful here, right? So this gets us features, And those features are almost like having some analysis, not just raw data, some analysis. It's saying, hey, here's what we found. Pay attention to these patterns and these patterns of patterns. And that lets these neurons that are in our dense layer learn better things, which will end up, getting passed to our output layer here. Okay, so we're going to run this, and we're going to run this, and we can see that there's not a substantive difference in things here, right? I don't think, I think I added a couple here. I think I changed the shape of something. I can't remember, but it's generally the same. Now I run the training here, 20 epochs here, and we'll see how it does. And what we're hoping to see is that the model is not overfitting, or at least it's overfitting later. And what that means is it's going to be learning and learning and learning, and it's still finding generalizable things before this happens here. Now, we saw it overfitting somewhere around epoch 6 or 7 last time. We saw it start to diverge. It looks like it's still bouncing around a bit. There's a 70% validation accuracy. So yeah, we're getting there around there, and it learned it a bit better. It's notice if you look at the training accuracy, it is not running away yet, although I assume it'll start too soon. Even with dropout, even with batch norm, if you train a certain number of epochs, it will happen eventually. So this model actually looks like it's doing a lot better, and we're getting a higher score, right, on our validation accuracy, and we're not getting this thing, our score here hasn't run away with it. Now, this model is not overfitting, right? What you're seeing here is what I would call model convergence. Now, this is a model you could probably get away with training for longer. We could probably up this to 30 epochs or 40 or 50. And if I was doing this on the job, that's what I would do next. Because I'd say, well, maybe we didn't get all the juice out of this lemon yet. Maybe let's squeeze it a little bit more and see if we can get this up to 75 or 76 or 80% accuracy. Maybe it just needs more time. At some point, time isn't going to be helpful anymore, and that's when the model will start to overfit, right? So it's kind of going, and it's going, and it's going, and this is a good sign. We have dealt with overfitting, right? And I'm going to actually pull that out because that is not correct. Cool. So let's train another version here that's a bit larger, right? And now what I've done is I've gone ahead and done 2 conv layers in a row before I max pool. This is another common pattern you'll see in deep learning here when you're using convolutional neural networks, is sometimes you do feature map, ReLU, so conv, ReLU, max pool. Sometimes you do conv, ReLU, max pool. That's totally fine too, right? And these are different things you can experiment with. There are different people that say, here's when you use one, here's when you want to use the other. We don't really know what's best yet. So you do have to experiment. You do have to practice with this here. So I'm going to run these real quick here, and we'll see what it looks like and how it comes out. And we see this is still quite a large model here. The number of trainable parameters actually went down a bit. And this is because we're changing the shape of it and kind of shrinking it a bit here. And the learnable parameters in some of these layers, as we change the parameters here, are a bit different. Notice I just did 64 across the board. I didn't play with 128s or anything else. Sometimes people shrink it to like, in the 30s or 256. I mean, again, this is up to you. You can really have fun playing around with this and seeing how high you can get this to go. Somebody asked, can I explain the dropout again? Does dropout remove features, and why does it solve the overfitting problem, right? So I would think of it like this, okay? You're a neuron in a neural network, right? And where are you getting your input from? Well, you're getting your input from all the neurons in the previous layer. And let's say neuron 1 in that previous layer never steers you wrong, right? You end up, it passes along a value, the information it gives you so valuable that you end up giving that a ton of weight and very little weight to all the rest, right? I'm going to 80% pay to attention to neuron 1, and then the other 1,000 neurons, I'm going to split that remaining 20% attention between them here, how much I care about what they're saying. And the problem is neuron 1 isn't always right. So when neuron 1 is wrong, you're going to be really wrong, right? So maybe there are important things the other neurons are saying. So what is dropout? Dropout is basically a percentage that neuron will actually not get passed along. It will not pass its info. It'll instead, it's like flipping a light switch. You turn it off for just that round. And because of that, right? So let's say you're that neuron that always listens to neuron 1 in the previous layer. Well, now neuron 1 got dropped out. What do? Well, you're still going to do your job, and you're going to say, you know what? Let's work with all the other neurons here. I have to pay attention to them. So let's see what I can learn from them. And you'll start to learn the relationships between them and when they're valuable and when they're not, right? There'll be times when neuron 1 is back, right? But you've actually started to pay attention to the other ones more, and you're learning maybe neuron 1 isn't 80% important. Maybe it's only 60% important. And these other ones are more important. Actually, neuron 3 and neuron 5 are really important, right? And they went up from 1% to 7% or something like that. So dropout just kind of varies what neurons are in the network at any given layer at a time. And dropout happens layer by layer. So I don't have to have a dropout layer on every layer. I just set it after a layer that I want to drop out. So, you know, this dropout is basically going to be dropping out on this one. I could remove this and it would just move right through, right? And I can have dropout on the others. Now, when you're doing inference, during training, those neurons get randomly turned on, turned off, right, with the percentage you have. So I set 0.5, it's like a coin flip. I've seen people do 0.8, I've seen people do 0.2. I've never heard of a good explanation as to when to use one or the other. We don't know yet. Maybe researchers will figure it out. We do not have a good overarching theory of neural networks and how they work and when to use one versus the other right now. So we just have to experiment. And so, oh, this model did a lot better. So with a bigger network, and larger feature extraction, we actually got up to 80%. That is really, really good. And we did it again in less than half of the time of one epoch from the time before. Okay, so that's really cool. That moved really fast here. Okay, now dropout itself, just to kind of talk about that, when it gets to inference, that's not useful, right? So we're training a model now, but at some point we're done training and it's game time, right? In that case, on the testing set, or when you're doing inference, right? So when you need the model for predictions, there is no longer neurons being randomly turned on and off. That's only during practice, only during training. In the real, and again, notice I didn't have to do anything to tell it to stop dropping out during testing or stop dropping out if I give you this one thing to predict on. TensorFlow is smart enough to do that for us, okay? So great question. I hope that answered it for you. And I'll be sure to drop some resources there. Gotcha. Akash, I just accidentally, there was a naming problem here. I believe I've gone ahead and fixed it. So you can just take a look back up here. I'll post again my copy here, but if you just look at the function that's throwing you the error, you'll find that like, oh, it's called GPU training history or something like that. So we've got these here. That's pretty good. We've got about 30 minutes left. I do want to make sure we run through how to use a TPU because TPUs are cool, but they are hard to work with. So we're going to move on to that, okay? So what do I do? Well, first thing I do is I go to runtime. I go to change runtime type, and I change this from GPU to TPU. Now, Google Colab gives you a certain number of hours free for GPU and TPU training, and then it kind of kicks you out. It says, you're past your limit here. You can pay for Google Colab Pro. I actually do. You can see the Pro logo right here. That's like $10 a month, and it gives you much more GPU, TPU hours, but it's not like it's not enough that you're going to build a company around it. If you're doing something in production for your company, and you guys use AWS or something like that, or Google Cloud, you're probably going to be better off using that. However, it's good to get practice with TPUs, and let's say I'm just working on something for like a Kaggle competition, I can use this. Side note, Kaggle also gives you free GPU and TPU hours, something like 30 a month. It's a lot. So it can really help you there, and you don't have to be working on Kaggle competitions. You can write any code you want in a Kaggle kernel, which is really helpful. So great for prototyping, great for doing things like that. So Let's talk about how to do this here. I've changed it to TPU. If I go ahead and just run the model, it would be back to like 2-minute epochs. What the hell's wrong there? Well, the TPU isn't, I didn't configure it, right? So this is very, very important. So I'm going to repeat this twice. And this is straight from the TensorFlow docs here. Once you run your import statements and import TensorFlow, the very next thing you need to do is you need to run this cell. Now this is boilerplate, okay? I did not write this. I pulled this straight from TensorFlow. That's what you should do too, okay? You do not need to understand this. You can, once you get deeper into this, you will, when you start to understand resolvers and strategies and things like that. But for now, just understand you're going to do this. You're going to grab a resolver. I mean, I'd literally just, if I were you, I would copy and paste this code from my notebook to your notebook whenever you're using TPUs. However, we'll see. For most things you need to do, GPUs are actually better. They're better supported. They're easier to use, and TPUs aren't faster until you're working at massive scale. So I'm going to run this cell, and we're going to see that it's going to grab, whoop, it crashed, session crashed. So let's restart that. Let me try that one. Well, it looks like it just did for me. So I'm going to run 1 and then 2. Session crashed for an unknown reason. That's a new one for me. Oh, I think it's better now. It looks like it's working. Here we go. Cool. And when you start to see this, this means the TPU is working. Okay. Now, these are the available hardware devices. Remember how we did that with like list devices for GPU? TensorFlow is doing this for TPU for us. We see there are 8 TPU cores and 1 worker. Awesome. This is great. So whereas we had 1 GPU before, we got 8 TPUs here to process these things here. So this is going to help a lot. Okay. Now, the difference is you'll see this code might look like, if you've spent some time doing some basic deep learning tutorials, this is going to look a lot more like what you've seen before rather than using TensorFlow data sets like we've done the last two classes here. The reason for that is that Google Colab, especially here, if you're working in Google Colab and you're using TensorFlow data sets, the data you need to pull from comes from a Google Cloud storage bucket. It does not want you to pull from local. It will throw you an incredibly confusing error that took me a solid hour to debug. So it is much easier to do it this way. Now, if you're loading your data set on your own and processing and all that here, which I assume you're familiar with, then you won't have any problems. But short answer, do not use TensorFlow data sets with this here unless you're storing stuff in a Google Cloud storage bucket. Then you can do it. And if you understand what I'm saying, you probably understand how to do it. If you don't, then don't worry about it. Just kind of keep moving it here. Essentially, as we're moving on here, I'm going to run these here. So we've got all that. This is just going to load our data set, and it's going to do some stuff. And I notice I didn't need to do this because of the structure of the data set. We're fine there. I commented it out, although that is pretty common stuff to have. Reloading my visualize function down here just so I don't have to go back up, scroll back up and do it. Now, this is where TPUs matter. And this might break, this should work. It's 50-50 sometimes with TPUs. But essentially, yeah, it's running the epoch. I think we're okay. So what matters here, yep, we're good. And that's better, it's fast. It's just not as fast as our GPU was here. What matters here is that, and what did I set our batch size to? I set our batch size to 64. Oh, that's part of the reason it's slower. You'll see here this with strategy.scope. And then my entire model creation is inside of this. It's nested within this within strategy.scope method call. I am defining the model. I am compiling the model. I am training the model, all right within inside this scope. That is the workflow for working with a TPU, with Google Colab or really anything with TensorFlow, right? With TensorFlow, this is what you have to write. Now, I'll make sure I add a link into the documentation, but if you just search TensorFlow 2 distributed training docs, there's a ton of details there. Some of it can be a bit hard to understand, and that's, I think, a good thing. TPUs, everybody wants to use the most powerful, shiniest, coolest thing. TPUs, while they are that, they are not useful to you all unless you are very comfortable with what you're doing in deep learning and you are working on a massive data set. So remember that model BERT I talked about? If you wanted to train that yourself on TPUs, it would take you weeks and about 60, your bill would be about $60,000 of cloud time by the time you're done, because that's expensive. So I think per hour or minute, I saw the statistics, I can't remember where, TPUs are 10 times more expensive than GPUs. And we see our GPU is actually way faster. So you're probably wondering, why is our TPU so much slower? I thought these things were supposed to be wildly faster than GPUs. The answer is, at scale, they are, okay? The reason that this is slower here is we're paying I would assume it's like a 10-second cost or something like that to do a distributed strategy, right? So if we have 8 workers working on this here, 8 different cores, well, we have to take some time and figure out who's getting what out of these 8. And so who's getting exactly what questions, and then we have to combine them back. And that's going to cost a constant amount of time, right? So if you're familiar with computer science, you might have heard of Big O, right? You hear like a constant time operation. Well, generally it's going to be, I don't know if it's constant time, but it's you can think of it as like a startup cost, right? In that the amount of your data you have, the distributed, it might be linear. That's fine. We can work with that, right? You can't do that as well. These things are faster than GPUs, but they seem slower when you're working on a smaller data set like CFAR10 and a smaller model. We're building a much smaller model here. This is still a toy by industry standards. A lot of models have in the billions of parameters. There, a TPU would blow GPUs out of the water. They're about 10 times faster. But that's only because at that size, TPUs are able to do many, many more computations, right? It takes a bit more setup internally. Not that, it takes a bit more setup on our end too. We have to write a little bit more code and understand what we're doing. But it takes a bit more setup under the hood. The TensorFlow is running for us. And here, the cost of that setup is greater than the benefit from using a TPU. And it would almost be faster for us to avoid the setup and just go straight to GPU. Not almost, it would be. So this is a common thing to think of here. So I would be aware of that when you're pitching to your boss, or maybe you got somebody on your team who said, hey, we really should use a TPU for this. They're great. And so, well, what's our problem? Is it worth it, right? And is this large enough that it's going to make a difference? And you'll get this by looking at the docs and studying up on this and playing around with it here. But the good part about Colab is that you can get practice with TPUs and GPUs without having to spend money. And that is crucial, because if you look at job postings for machine learning engineers and data scientists, if they're asking for TensorFlow, you can guarantee that they don't mean, can you run TensorFlow on a CPU? They're talking about, can you do this with hardware acceleration? Okay. So this is a very wonderful skill set to have. Let's talk about some of the issues you might run into here. Okay. I'm gonna, once this runs and we see how the model comes out, I'm gonna go ahead and change some code, and we're gonna break it on purpose. Okay. And we're going to see what do some of these errors look like when using a TPU. Okay, and if I run this, okay, and yeah, it actually doesn't do as well as our model we did before. We used a different architecture and things like that, but it's all right. It's not great. It's not horrible. It's not great. It's right where we were before, but that isn't the whole point of this here. So let's talk about some of the things you need to worry about when working with this here. The first is that it is really, tensor processing units are really, really fickle about data types. So here, I'm going to go ahead and remove that, and whoops. And I'm going to go ahead and move. Actually, let me do this. I'm just going to comment this line out. And I'm going to comment this line out because all that was doing is a cast. So if I rerun this, and I rerun this, and let's actually go, and in this cell, let's look at the data type of y-test here. So y-test is a list. So if I do type, and I call for y-test, right, it's going to give me a list, right? It's a NumPy ND array. But let's actually look at the data type of the first thing inside of that. Or excuse me, it's a list of lists, that's why. Okay, there we go. So this is an 8-bit integer. It is a uint8, an unsigned 8-bit integer, right? And that doesn't seem like that big a deal, a 32-bit integer or an 8-bit integer, but some of the things that make tensor processing units so powerful is they are very, very fickle about data types. So they have their own data types like a bfloat 16 and systolic arrays and all this stuff that allow it to do this crazy stuff at scale in the hardware, at the hardware level. And because of that, the data types you pass in, you have to do it a certain way. So this is an error I spent way too long trying to debug. Is going, what the hell? And I'm going to show you guys, we're going to cause this error, and I should get it right here. And it should give me the most arcane, useless error message you've ever seen. Okay. Op kernel was found, but attributes didn't match. Requested attributes, DT uint8. What the hell is all this? Well, that's because all of these workers are throwing things back here and what it expects here. So the issue is that it's an unsigned 8-bit integer. I took a little bit of time to Google the errors. And again, what do you do? And you're going to run into these in the real world. If you try working with tensor processing units, you will run into weird arcane errors like this. So what do you do? Well, the first thing I did is I tried Googling, these specific errors. I Googled tensor processing, Google TPU Colab error, and you just kind of get used to Google fooing it, right? And what I found is that, well, in a message section of GitHub about, somebody had this error and they posted to that here, that, oh, you have to cast it to 32-bit integers. It doesn't say that anywhere, but, except deep in the documentation. But if we do this and we rerun things, we will see it turns out just fine. And now if we run this, we see it's a uint32. And if we go back and rerun this, it'll work, right? So this is kind of where we're at. That is one very common error. You'll get another common error again if you try and use TensorFlow data sets. So if I rerun the section from above and create that and try and pass those in, we'll get a different kind of error. And that's only because it hasn't set up a local file system on our machine. It needs the Google Cloud file system. So there's a lot of very weird errors, a lot of very weird edge cases that you will get with TPUs, you will not get with GPUs. If you need TPUs, you can use them. There's a lot of great documentation in the next couple months or years. I'm sure there will be an amazing amount of documentation as both Google and Amazon and Microsoft can't be far behind, are betting hard on these here because they do make, at really industrial scale AI, it makes a very big difference. For what we're doing to practice, not so much, okay? Or the types of projects we might be working on, not so much here. So it's good to have that context here. And again, if you're interested in how they work, I will make sure I post a great video from Kaggle. It's about 8 minutes that explains how TPUs work under the hood and why they're faster overall, okay? So that's everything for this class today. I will end by answering some questions here. We got about 18 minutes, so I'm happy to answer any questions you might have. I do see one from Roy. I'll get to you in just a second. Before we do that, let's talk about what you've learned so far and what we're going to teach in the next class here, okay? So in the last class, we learned about TensorFlow and deep learning. In this class, we learned about some more practical use cases for things that you'll have to worry about in deep learning, like your model overfitting, like convolutional, like feature extraction via convolutional neural networks. We also learned about hardware acceleration, which with deep learning is a must-have. It's phenomenal. So now that we've got all this, we're going to start in our next class, in class 3, we're going to start adding behavior to our models, right? we're no longer worried about how to train our model. That part, we can do that, right? Or how to architect it. What layers should we use? Well, we might have some questions, but we know enough we can figure it out, right? And the rest comes from practice or some really good classes like the kind we offer. So what do you do next year? Well, you start worrying about the things that true deep learning engineers and researchers worry about, which is hyperparameter tuning and callbacks and things like that. So next class, we're going to spend some time really talking about workflow. We're going to talk about how to create pipelines that kind of do everything start to finish. They work well. We're going to talk about one of the most important parts of deep learning, which is hyperparameter tuning. Specifically, what is probably the most important hyperparameter in deep learning, which is the learning rate. And finding the correct value for a learning rate can be the difference between 30% accuracy and like 80% accuracy. So we're going to talk about some advanced methods for that, like using learning rate decay. We're going to talk about how to use a learning rate scheduler, how to use cyclical learning rates maybe. We're going to talk about things like, you know, right now we're just kind of saying, well, train for 10 epochs. And if that doesn't work, train for 20. And if that works, train for 30, and so on and so forth here. But it would be easier for us to say, well, train until our validation accuracy stops going up by a certain amount. And we'll learn how we can do that with early stopping. So we can stop at epoch 6 and not train to epoch 50, saving ourselves time and, more importantly, saving us money, because again, training in the cloud costs money. So we'll learn how to use callbacks for that. We'll learn how to use callbacks like TensorBoard to be able to inspect our models. So far, we've been making these little rinky-dink graphs in Matplotlib. And we're going to see, well, actually, Google has included this massive web server that does the most incredible work for helping us visualize the weights of our model, maybe some embeddings, maybe you know, what the different scalar values are, like accuracy or detecting overfitting. We're going to find TensorBoard is absolutely awesome, and you're really going to enjoy it. So we're going to learn how to use those callbacks. We're going to learn how to write our own. So that it can do certain things like trigger this behavior if it's done training. That might be something as simple as, okay, when the model's done training, save the best version of it, or something as handy as, hey, the model's done training, send me a text message via Twilio, or send me a message on Slack that my model's done training. So that way, you know, you can go stand by the coffee filter and hang out until your model's done, okay? This was a great class. You guys did very well. Let's answer some questions. So I see, Roy, your question is, what are the main differences and pros and cons between PyTorch and TensorFlow? And my answer is that there's not a lot of differences. Researchers tend to use PyTorch, whereas TensorFlow is king in industry, right? So PyTorch, now again, it used to be that PyTorch was used by researchers because it was easier, and TensorFlow was used by professional developers because it was harder to do, but they were better engineers and they were faster. TensorFlow was faster. Now, both of them have come more towards the middle in the recent year here. TensorFlow has realized they're missing out on the research market, right? And if all the people coming out of college or training are using PyTorch, it may not bode well for them. So what have they done? They did all the changes we talked about last week, which was things like change the amount of configuration that's needed. We don't need to create a graph. It does that for us. It characterized everything. It made it easier to do a lot of things. To me, I think I do know both of them, and I like TensorFlow 2 right now better. I am a bit biased because I learned first on Keras. But PyTorch is good if you're doing like research. I'm not doing research, I'm doing production stuff. So it is fast for me to prototype on these things here. I'm a huge fan of TensorFlow too, but I'm also a big fan of PyTorch. Really, you can't go wrong with either. My advice to you would be that, and again, PyTorch is also super fast now too. It's very well optimized. Now, it's not as optimized as for things like AWS or Google Cloud, obviously, because that is TensorFlow's whole game. That's their whole métier. That's their specialty. PyTorch is just getting into that. So you can run it, and people do run production loads in PyTorch. There are thousands of companies that do that. You absolutely can. But I find the documentation, the examples, and all that other good stuff are easier for TensorFlow. So hopefully that gave you a good answer there. You really can't go wrong with either. I would definitely encourage you to take a look at both and see what works best for you. Olayinka asks, when will the recorded lectures be made available? The answer is shortly after this here. So we do record these, and if you've ever done a recording with Zoom, they're not available to us immediately after. Zoom has to do some pre-processing of them on their server. The longer the video, the longer the pre-processing takes. So realistically, it takes a couple of hours for it to do that, and then it's made available to us. When it's made available to us, we add them out shortly. So we will send an email when all of this is ready and live and let you know, so be on the lookout for that. And we'll add it to the folder, okay? So it'll be in the folder where we have all this good stuff here. We'll make sure those links are good to go and you see them, okay? So, and if you do have any questions, you can certainly shoot us an email, and we're happy to make sure we get those to you, okay? If there's any other questions here, feel free to fire away. Otherwise, we'll wrap this quick. Thank you all so much. Rob, you're very welcome. Thank you for coming. You're very welcome, Graciano. Thanks for joining here. We'll give it one more minute for any questions to get typed in, and if that's all of them, we'll wrap. So we'll give it one more minute for any questions. All right, I guess that's all the questions. Well, thank you all so much for joining. And again, we hope you can join us next week for class 3 here, where we're really going to start to ramp and do some cool stuff with all our new deep learning methodology. So thank you so much, and have a great day.